How does kVA affect power factor correction for engineers? If you are curious about how kilovolt-amperes impact power factor correction for engineers, you are in the right place. Let's break this down in a simple way. Kilovolt-amperes, or kVA, is a measure of apparent power in an alternating current circuit. It combines both real power, measured in kilowatts, and reactive power, measured in kilovolt-amperes reactive. Power factor, often abbreviated as PF, is the ratio of real power to apparent power. To put it simply, it tells us how effectively electrical power is being used. Power factor correction is all about improving this ratio. When we reduce the reactive power component, we lower the kVA needed for a specific kilowatt load. This is important because kVA affects the current flowing through the electrical system. Higher kVA means more current is needed, which can lead to increased losses and the need for larger equipment like transformers and cables. For engineers, understanding this relationship is essential. When power factor correction capacitors are added, they help reduce the reactive power. This, in turn, lowers the kVA demand on the system without changing the actual useful power. For example, if you improve the power factor from 75% to 95%, you could see a reduction in current flow by over 20%. This allows transformers and distribution lines to operate more efficiently. Installing power factor correction capacitors near inductive loads, such as motors, is a common practice. These capacitors locally supply reactive power, which reduces the amount drawn from the utility. This not only decreases losses in transmission and distribution, but also helps avoid penalties from utility companies that charge based on kVA demand. Moreover, improving the power factor can help defer costly upgrades to electrical equipment. By lowering the kVA demand, engineers can optimize system capacity and reduce energy losses, leading to better overall power quality in power generation and transmission systems. In summary, kVA plays a significant role in power factor correction. Reducing the reactive portion of power lowers the apparent power demand. This principle is vital for engineers as they work to improve efficiency and capacity in electrical systems.